Hello and welcome to this Haas Tip of the Day. British inventor David Massell, way back in 1899, teamed up with an American company to create and develop the flashlight, the electric torch. Now, Eveready, just a few years later in 1907, came out with what would become the most popular battery in the world, the AA. And even today, these AA batteries, this size, accounts for more than half of the alkaline batteries sold worldwide. So why am I telling you this? Well, it's because I can imagine Mr. Eveready standing in front of a crowd of thousands of people saying, "Behold, the flashlight," and nothing happens, no light at all. He might say to himself, "What's going on here? Wait, I've got it. I may have put the batteries in backwards. One moment." Flips the batteries around, puts them back in, click, 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 and there we go. Behold, let there be light. We've all done it, but it's not a big deal. We've changed out the batteries on something, flashlight or remote control, and the thing doesn't work. So we take the batteries out, flip them around, put them back in, and we're all good. But on a CNC machine, if an operator were to load the part backwards or to put in raw stock instead of some Op-10 finish part, he's definitely going to scrap that part and he might crash the machine. So that's what this video is all about. Right now, we're going to give you some code. We're going to show you how to use your probe to guarantee that a part is loaded correctly each and every time. So stick around. Everything for me begins with my setup sheet. So check this out. I've got a block loaded up. Now, if you're tightening up those tools by hand, so the question is, why, after 100 years, do we still have batteries that we can put in backwards? Why is this even possible, right? Well, there's very low risk involved with putting a battery in backwards. If the risk was higher, let's say that you would be electrocuted if you were to put a battery in backwards, then I guarantee you that some young engineer would have designed that possibility out of the flashlight. In fact, even with a cordless drill, they have made it impossible for you to put the battery in backwards. You just can't physically do it. That kind of mistake proofing is called a Poka-Yoke. Now, I know it's Poka-Yoke or Poka-Yoke, I don't know. We've always called them a Poka-Yoke in the shops that I've worked at. So forgive me. You can straighten me out in the comments. Poka-Yoke. It's a Japanese term that started off as Baka-Yoke, which means idiot-proof. But that seemed a little bit cruel, so we've moved away from that, and now we just go with Poka-Yoke. Now, if I'm speaking to operators directly, I'm going to say that it is 100% your responsibility to load your parts correctly. Read the setup sheets, that's your job. Now, if I'm speaking to CNC programmers, or a manufacturing engineer who's designing a fixture, we should be designing fixtures that don't even allow the operator to load the parts backwards. We need to mistake-proof these things. Now, typically, we'll mistake-proof a fixture by adding a dowel pin in such a way that the part is blocked from being loaded incorrectly. But in a lot of cases, using a probe to check our part orientation will make more sense. So here is our part. It's a fake part, not a real part. But in this example, we need the operator to load the part with that large hole to the left. If they were to load the part with the large hole to the right, then bad things would happen. So we've written some code up here, and we're going to show you this code in a minute, that's going to probe the part. And if the part is loaded correctly, then the program just keeps running, machines the part out. But if the part is loaded incorrectly, we're going to custom write a message that'll pop up on the screen and hopefully give them enough information to solve the problem quickly and get back to making parts. Now, you should recognize these first few lines of our code. If you don't know what these codes mean, if you haven't used them before, don't program your probe. You're not quite ready yet. You need to be able to program a drill before you can program the probe. But beyond that, it's pretty simple, and we're going to show you how the probe works right now. Our next line of code is simply turning the probe on using a G65 P9832. Now, this is an important line of code. In fact, let's enter this into MDI and I'll show you what it does. Okay, so G65 P9832 are up on my screen. I'm going to press cycle start. My spindle probe is now on. The green lights are flashing on it. With the probe on, I want to show you something here on the diagnostic page. So this machine is a next-gen control. On the diagnostics page, I'm going to go to the I/O tab, and I'm going to type in probe and press F1. This is going to show me all the input outputs for the probe. And there's one listed here, input 17, which says probe signal. Probe signal. If you were on a classic Haas control, you would see this same thing on the input-output diagnostics page, but it would be called skip signal. Same exact thing. So with my probe on and our probe signal showing here, it says value of 0. I'm gonna flick that probe. So we've shown you the spindle probe really quick, not that we're doing this today, but you can do the same thing with your table probe. We can command a G65 P9855, and that will turn the tool probe, the table probe on, and G65 P9856 will turn that table probe off. You can check that the same way. You can tap it with your finger and see that input change. Now this brings us to our G65 P9810 protected positioning move. This allows us to move our probe safely from point to point. Now normally, if the probe makes contact while the P9810 sub is active, the machine will stop and the control is going to give us a 1086 path obstructed alarm. Now this is a good alarm. This is typically why we use a 9810. But we're going to use this 9810 code a little differently today. If we add an M1.0 to this line, not an M01, but an M1.0, the 9810 transforms into something magical, just incredible. It becomes a really powerful programming tool to detect part orientation. Two important things happen when we run this code with an M1.0. Number one, the machine will no longer alarm out when that probe makes contact. That 1086 alarm was good, but it's not descriptive enough for our application. And secondly, the program is going to set a flag for us using macro variable 198. Now this is important. When 198 is set to a 0, that means that the probe was not triggered. And if the macro sets variable 198 to a 7, that means that the probe was triggered. Variable 198 is typically used on the classic control, and on the next-gen control, we'd use variable 10,198. They're kind of synonymous. We don't directly set variable 198 to a 0 or a 7 in our program. It happens automatically when the P9810 Renishaw macro is called with an M1.0 on the line. Now you can download the Inspection Plus manual from the Haas website and check it out for yourself. 0 means no probe triggered, and a 7 means probe triggered. That's just the way Renishaw set it up to help us out. We now have all of the information we need to create our own pound 3000 user-generated alarm. We can alarm when we want, and we can display the alarm message that we create. We can have this happen if the probe is triggered or if the probe isn't triggered. That's a 198 equals 7 or 198 equals 0. So here's our if statement. If pound 198 does equal 7, if that's true, then we're going to go to line number N3000. And then we can run our alarm code, where we've got an alarm, user-generated alarm, waiting for our operator to tell them that they've loaded the part incorrectly. That's it. That's the entire program in those few lines. We can even add an M130 media file, a media path to the program, if we want to give the operator some more information to help them through the problem. Now, I took the time to explain every bit of this code so you'd really understand it, because you're going to have to write your own custom macro because every application is slightly different. So we found a feature on a part that can be measured, and then we probed it. and then we wrote some macro logic to alarm out if the part wasn't in the position that we'd like. Now this same style of macro can be applied to a part like this one, where you run both the first and the second operation in the same vise. With one probe hit and the code we showed you, you can tell if the part is loaded correctly, whether it's running the first operation or the second. And we can give the operator instructions through a custom alarm telling them if something is off. It's all about avoiding mistakes. We've made a lot of videos that are related directly to the topic that we discussed today, and we've added links to those videos in the description, so be sure to check those out. And also, be sure to click on the like button. That lets us know that you find value in these videos. Thanks for letting us be a part of your success, and for watching this Haas Tip of the Day.